So hey guys, a very good day to you all. In this video, we are going to understand the integrated rate law for first order reaction. Now guys, the first question that must come to your mind is that what is the use of integrated rate law? We already know how to find out the rate of the reaction and we already know the differential rate law. Then why do we require this integrated rate law? So the simple answer for this is we require this to find the concentration of reactant for different times, which means that you can find out the concentration of reactants after 2 seconds, after 4 seconds, or after any time that you want. So this is the basic application of integrated rate law. Now to understand this integrated rate law, let us consider a simple equation over here. Now in this equation, as you can see, A is acting as a reactant and this one is nothing but the stoichiometric coefficient. Now, as we all know, the basic formula to find out the rate of the reaction is nothing but 1 upon stoichiometric coefficient, that is nothing but 1 in this case, into change in concentration of reactant, and here reactant is nothing but A divided by change in time. And according to the rate law, we get another formula for rate of the reaction, that is nothing but K into molar concentration of A raised to the power 1. Now as you can see over here, K is nothing but the rate constant and we have raised the molar concentration of A to the power 1 because we are considering first order reactions over here. Now guys, if I do not know how do we get these two formula or these two equations, then you need to watch my previous videos. The link of the playlist is given in the description box below, or you can simply click on this I button which is present on the right top corner of your screen. Okay, now moving on, if you observe this equation number 1 and if you observe this equation number 2, the left hand sides of both the equations is same, and since the left hand sides of them is same, therefore the right hand sides of both the equations will also be same. So from equation number 1 and equation number 2, this is what we get. So we have found out a relation with the help of equation number 1 and equation number 2. Now what I'm going to do next is that I'm going to multiply this equation by a negative sign. Okay, so let's multiply this whole equation by -1. Okay, so this is what we get after multiplying by -1. Now what I'm going to do next is that I'm going to shift this dt to the right hand side, and let's shift this molar concentration of A raised to power 1 to the left hand side. So after doing so, this is the equation that we get, and let us name this equation to be equation number 3. Now let us keep this equation aside for next two or 3 minutes. Okay, now let us have a quick look at our equation again. So this is our main equation that we have considered to understand the integrated rate law. Now guys, at time is equals to 0, which means that your reaction has not yet started. So since your reaction has not started, therefore we have considered time to be 0. We assume the molar concentration of reactant A to be A0. So before the start of the reaction, let's say the concentration of reactant is A0. Now obviously, since a reaction has not started, therefore the concentration of products will be 0. Okay, now your reaction starts, and after time t1 we assume that the observed concentration of reactant is AT. Okay, so after certain time t1 we have assumed the concentration of reactant A to be AT. Now my one simple question to you all, between A0 and AT, which will be greater? Which concentration will be greater? So the answer will obviously be A0. Why? Because as time passes, some amount of reactants get converted into products. Therefore, the amount of reactants decreases. And since the amount of reactants decreases, then obviously guys, the concentration of reactants is also going to decrease. So here A0 will be greater than AT, and after certain time t1 we have assumed that the concentration has become 80, so it has decreased from a0 to 80. Now guys, let us again consider our equation number 3. Now what you need to do next is that you need to apply definite integrals to this equation number 3. So applying definite integrals on both the side for this equation number 3. Now when you apply the definite integrals, you need to be careful about the lower limit and the upper limit. Now let me explain one thing again, one thing over here. Now on this right hand side, you are going to apply limits for time. The upper limit and lower limit will be with respect to time. Why time? Because you are integrating with respect to dt. T is nothing but time in our case. And on the left hand side, the upper limit and lower limit must be with respect to A. That is nothing but here molar concentration of A. So the lower limit and upper limit must be with respect to concentration of A. Now, at time t is equal to 0, what was the concentration that we have assumed? We have assumed the concentration to be A0. Therefore, I write A0 over here. And after time t1, I have assumed the concentration to be 80. I hope you have understood this part. This is the most important part of the complete video. Now, further on simplifying this equation, if you observe this minus k, this k is nothing but a rate constant. So it is a constant value. So let us take this minus k outside of this integral. Okay, so taking this minus k outside of the integral, and this is what you are left with. Now, the limits are going to remain as it is. Now, integration of 1 upon x. Integration of 1 upon x is nothing but log x. And here, x is nothing but concentration of A. And here, integration of A is not, integration of 1 is nothing but x. And here, you are integrating with respect to dt. Therefore, here it will come t. Now, this is what we get. And you need to consider these limits also. Otherwise, you will forget to consider this limit. Now, one important point which you must notice over here, and many of the students make mistake over here. Here you are going to consider log to the base e. Whenever you integrate, you are going to get log to the base e. Okay. Now, further on, just substitute this limit. I hope you all know how to substitute this limit. And after substituting this limit, this is what we get. I just substitute, instead of concentration of A, I substitute AT minus A0. As simple as that. And here, instead of T, you need to substitute T1 minus 0. Upper limit minus lower limit. As simple as that. Now further on, log of A minus log of B. Log of A minus log of B is nothing but log of A upon B. And further on simplifying this, this is the equation that we get. Okay. So I hope everyone is clear up till here. Now further on, what I'm going to do next is that, as you can see over here, I have just shifted the negative sign. Okay, I've just multiplied the whole equation by minus 1. So multiplying the whole equation by minus 1, this is what we get. Now in our next step, what we are going to do is that we are just going to shuffle this numerator and denominator. I hope you all know the property of log. So if you want to take the if you take negative common out of this, then the numerator and denominator get exchanged. So you have taken negative common out of this log, and negative becomes positive. Therefore, you are having a positive log over here. Okay, I hope you all remember this property of log. You all know this property of log. We have just shifted the numerator and denominator. Now, further on moving, guys, what we are going to do next is that just shift this T1. Okay, just shift this T1 to this left hand side. Okay, shifting this T1 to the left hand side, this is the equation that we get. Okay, now this is the correct equation and this is the actual equation. But guys, whenever we do calculations in your examinations, we do calculations with the help of our log book. And in our log book, all the values are with respect to the base 10, log to the base 10, but we are having log to the base e over here. So for our simplification of calculations, let's convert this log to the base e to the log to the base 10. Now when you do so, you need to multiply by 2.303. So when you multiply by 2.303, you get log to the base e converted to the log to the base 10. You have just converted the base, and the rest of the formula is going to remain as it is. And guys, this whole thing that you have got is nothing but your integrated rate law. And actually this integrated rate law helps you to find out many values. You can find out the rate constant with the help of this, and by just substituting the time. And you can also find out the initial concentration. You can also find out the concentration after certain time, after 5 seconds, after 4 seconds. I hope you'll remember what is this AT. AT is nothing but the remaining concentration after time T1. You can substitute the value of T1 as per your convenience. Now guys, if you observe this formula, on the left hand side we are having K, which is nothing but the rate constant. So let us find out the units of rate constant for first order reaction. So as you all know that this integrated rate law is applicable only for first order reaction. So obviously the unit of K, whichever we get, will only be applicable for first order reaction. Okay. Now for units we use the same formula, and in this formula if you observe, in the numerator we are having concentration, and in the denominator also we are having concentration. So both of them are going to cancel their units, and this part is just useless for units. So the only part that we can consider for units is this much part, 2.303 upon T1. Out of this also, if you observe, 2.303 has no units. Okay, it is just a constant. And T1, which is nothing but time, and time is in the denominator. Therefore, we say the units is nothing but time inverse. Okay, so unit is going to be time inverse. It can be in seconds, minutes, hours, whatever you consider. Okay. Now further on, guys, let us understand the half-life of first order reaction. Now what is the half-life? The meaning of half-life is the time required for the concentration of reactants to become half. I repeat myself again. Half-life is the time required for the concentration of reactants to become half. Okay, so for that also we are going to use the same formula as we have considered before. Okay, now in this, what is this AT? AT is nothing but the concentration at time T1, as we all know. So as we all know that we want this concentration to become half, and if it wants to become half, it must be half of A naught. Why it must be half of A naught? Because A naught was the initial concentration we have taken, and we want the half of it. So AT should become half of A naught, and at that instant we want time T1. Okay, so using this, just substituting AT is equals to A naught upon 2, and by this simplification, this A naught gets cancelled. You are left with something like this, and we all know that the value of log to the 2 to the base 10 is nothing but 0.3010, and this T1 as it is in the denominator. And this is the formula that you are going to use for finding the half-life. So using this formula, if you know the value of K, you can easily find out the value of T1. And in this case, for half-life, this T1 is the time required for the concentration of reactant to become half. Okay, I hope this was clear, guys. So, and if you observe over here, half-life is independent of initial concentration. In this formula, can you see initial concentration wherever? No. So half-life is going to be independent of initial concentration. If you observe over here also, before we have nowhere used initial concentration, because this initial concentration gets cancelled out. See, this gets cancelled out. Therefore, it has no role to play when it comes to half-life. So guys, I hope you have liked this video, and if you have liked this video, don't forget to subscribe to our channel and go check out my channel where I have uploaded physics and chemistry videos. They might be helpful for you guys. Thank you for watching this video.